Effect of using PCM as cooling medium in different types of heat sinks. Abstract engineers, those who are tasked to design modern electronic devices, face many issues related to smaller packages with more components. This leads to more power dissipation. Hence, cooling of devices becomes a necessity. Heat sinks are inevitably used for thermal management of the electronic devices. This paper compares temperature variations from inlet to outlet for different types of heat sinks placed in air and fluid domain, and ways to increase efficiency of heat sinks using phase change materials are investigated through simulations using Ansys Fluent simulation tool. Keywords: heat sink, temperature, PCM, phase change materials, thermal management. Introduction. Electronic equipments were traditionally used in industrial applications. But in modern life, they have made their way in almost all accessories frequently used in day-to-day life to costly industrial appliances. The power consumption and hence heat dissipation is one of the areas to be investigated, as inappropriate heat dissipation may lead to many problems like higher temperature, which leads to more power leakage and hence decreases device reliability. Standard cooling techniques like fan are not effective for heat dissipation in small packages. So, many types of heat sinks are used to reduce the temperature and increase efficiency of device during continuous operation over long periods. In present work, thermal management of chip is made using aluminium heatsink. Aluminium is lightest, easy to handle and to install. At the same time, it has high thermal conductivity and good air pressure resisting capacity. Upon everything, it has low cost with high efficiency. Evolution of cooling techniques started from using fan as a cooling source. With time, different cooling techniques were invented. Active cooling requires external devices for heat transfer. Components like fan are used when natural convection is not sufficient to remove heat. 2. Passive cooling uses radiation or convection for heat transfer. 3. It does not need power for heat transfer. X. Heat sinks. In current market, heat sink plays an important role as a cooling substance. A heat sinks. It is a thermal device and a heat exchanger, which absorbs heat from electronic devices and transfers it to other medium by conduction, where the medium may be air or phase change material, PCM. In this work, results of both air and PCM as heat conducting medium are investigated. There are many types of heat sinks in which cylindrical pin fin, square pin fin and bonded fin type are most prominently used for. Pin fin type heat sink. Pin fin heat sink differs from other heat sinks as it has pins that are extended from its base. These pins are of various shapes like elliptical, cylindrical, and square. Pin fin type heatsink is more efficient than bonded fin heatsink because it allows coolant to flow on almost all the parts of its surface. In case, if fluid medium is used as coolant, they perform in better manner when placed in tilted position, as this position helps fluid to flow through heatsink easily too. They are perfect for spotlights, shot lights, as they are adjustable. With increase in number of pins, efficiency increases as it allows more coolant through it. This heatsink is cheaper. It has one disadvantage. They can be used only where surface is in direct contact with coolant nearby. 5. 2. Bonded fin type heat sinks. This type of heatsink is made up of aluminium or copper plate first and then combined with heatsink with grooves. One advantage in this type of heatsink is different materials can be used for plate and fins. Heat dissipation ability is good. Main disadvantage is it provides less surface area for cooling and is costly. 3. In present work, aluminium is chosen as heatsink material, and results of cylindrical pin fin type, square pin fin type and bonded pin type heatsinks are studied through simulations and compared with both air and fluid as cooling medium. B. Simulation setup. Heatsink measuring 20x20x 6 mm is taken for study. 3 types of heatsinks, i.e. cylindrical pin fin type, square pin fin type and bonded pin type heatsinks, are compared and results are recorded. The experimental setup shown in figure 3 is placed on an electronic chip. The design is made using SolidWorks heat transfer technique. The heat produced by electronic chip will be absorbed by heatsink and will be transferred through conduction, and then heat will be carried out by the fluid by convection and radiation. 5. Conduction, convection, and radiation are 3 processes that take place in heat transfer process. 1. Conduction, transfer of energy in the form of heat from higher energy to lower energy substance. 5. 2. Convection, it is heat transfer between fluid in motion and a solid surface. 5. 2. Ansys fluent modeling. This study is done using Ansys Fluent simulation tool. For the sake of design, testing, and operation, many multi-physics engineering related softwares are developed and marketed by Ansys. Ansys Fluent is a type of software where larger structures are sectioned into small components where each are modeled and tested individually. A user may start by defining the dimensions of an object, and then adding weight, temperature, and other physical properties. Finally, the Ansys software simulates and analyzes movement, fatigue, fractures, fluid flow, temperature distribution, electromagnetic efficiency and other effects over time. 3. Simulation process. In present work, the solution is updated every 0.01 second with 50 iterations per time step. In this study, heatsink is placed in air as domain which has one inlet and one outlet and is studied at room temperature of 15 C to make our study more effective. Any temperature can be taken as room temperature. This temperature may further change at the inlet due to the influence of heat of heatsink. The heatsink shown in figure 4 is cylindrical pin heatsink placed in above mentioned conditions. Simulation process has 5 steps. 1. Geometry. In present work, SolidWorks simulation tool is used to create the geometry shown in figure 4. So, the geometry file is imported from SolidWorks. 2. Meshing. The modeled geometry will be meshed. There are many shapes in meshing like hexahedron meshing, triangle etc. The mesh influences the accuracy, convergence, and speed of simulation. Hence meshing is important factor in Ansys simulation. Fig 4. Heatsink placed in air as cooling domain. Fig 5. Part of mesh. 3. Setup. Required input information like temperature, pressure, type of initialization, mesh interfacing etc. are given here. 4. Solution. The Ansys simulation tool calculates solution by using finite element analysis, FEA. 5. Results. The results will be pictorial representation, which helps the user to understand it easily. The below shown pictures, Figure 6 to Figure 10, Figure 13, and Figure 14, are results for present work. In present work, the following conditions are chosen for all 3 types of heat sinks. Time, transient analysis is chosen, as it helps to get detailed output and also helps to show gradual variation of temperature from inlet to outlet and temperature difference between top and bottom of heat sink. Energy, it is turned on as heat is also a form of energy and we need to get temperature output. Material, air as domain and aluminium as heat sink material. Cell zones, here we have 3 cell zones namely, chip, which is considered as heating source, heat sink and domain where heat sink is placed. The following states must be chosen. Chip, solid. Heat sink, solid. Domain, fluid, in Ansys, even air is considered as fluid. For chip, a heat flux source is provided so that it can heat and allows heatsink to absorb heat. Hence one energy source is provided for chip. Boundary conditions, here inlet is selected as velocity inlet as air enters inlet with a certain velocity. The magnitude of velocity is taken as 1 m/s. The outlet is selected to be pressure outlet. The atmospheric temperature is selected as 15 C. Any temperature can be selected as atmospheric temperature. Mesh interface, in this work, we have 2 types of material. Air, which Ansys considers as fluid and another one is solid. Ansys is very much efficient to make difference between these 2 materials during meshing. Hence we have to couple those 2 so that Ansys can make difference while meshing. This work is done during mesh interface. Here coupled wall is turned on so that Ansys can find out temperature of both solid and liquid without any problem. Solution initialization, hybrid initialization is selected for more accuracy. It uses boundary conditions before giving output. Run calculation. Time step size equals 0.01. Number of time steps equals 200. Maximum iterations equals 40. So, Ansys is instructed to do at least 40 iterations if convergence is not reached. Calculation activity, here the file where data is be saved is chosen along with all the quantities which is to be calculated. In this work, temperature, pressure, and velocity is chosen. Frequency, time step 3. This is because, the output will be calculated for thousands of times and there is no need to save all data. This is the instruction for Ansys to save one output after every 3 outputs. After giving all the instructions to Ansys, the results provided by Ansys are as discussed below. For results. Temperature distribution in different types of heatsink placed in air medium is as shown from Figure 6 to Figure 10. Left-hand side in cylindrical fin pin type of heatsink, Figure 6, has inlet and right-hand side has outlet for cylindrical fin pin heatsink. As mentioned earlier, the atmospheric temperature is 15 C. The blue part represents cold air at temperature 17.8390 C is entering heatsink. The increase in temperature by 2.8390 C is due to the influence of temperature of heatsink which is placed inside air domain. The temperature of air increases due to convection and hence the heat is transferred from heatsink to air, which is cooling medium. The right-hand side has red color and indicates the air coming out is hot, i.e. 21.650 C, and hence heat is removed from both chip and heatsink. The temperature at inlet is 17.8390 C and outlet is 21.650 C. Hence the heat is removed effectively. Similarly, the figure 7 shows temperature simulation results for square pin fin heatsink placed in air as cooling medium at same room temperature, i.e. 15.0 C. The temperature at inlet is 17.8390 C and outlet is 20.30 C. Compared to readings of cylindrical pin fin type of heat sink, heat removal is 1.350 C less here. Hence the heat removal is less effective than cylindrical pin type heat sink. Fig 7, temperature distribution in square pin type of heat sink. The figure 8 shows temperature distribution in bonded fin heatsink with air as cooling medium at room temperature of 15.0 C. The temperature at inlet is 17.8390 C and outlet is 19.030 C. This type of heatsink has less space in between fins for air to pass through it. So air cannot cover complete base of heatsink compared to pin fin type. Hence blue color at right hand side shows the air coming out of heatsink is not so hot, i.e. 19.030 C compared to inlet temperature, i.e. 17.8390 C. It can be observed that the rate of heat transfer from bonded type of heatsink is less when compared to cylindrical pin fin type of heatsink by 2.620 C, and hence this type of heatsink is not so efficient in heat removal from heating source compared to cylindrical pin fin type of heatsink. To calculate convection heat flow, let heat transfer coefficient, H, for forced convection of air be 100 W/m2.K referring to table in Table 1. The heat flow for different types of heatsinks are as in Table 2. The heatsink placed in air domain removes heat from heating source. From above table, it is evident that the temperature difference between inlet and outlet is decreasing from cylindrical type of heatsink to bonded fin type of heatsink. The cylindrical pin fin type of heatsink reduced the temperature of chip by 3.8110 C. Similarly, square pin fin and bonded fin type of heatsink reduced the temperature of chip by 2.4610 C and 1.2010 C, respectively. Hence cylindrical pin fin heatsink acts more effectively in heat removal than square pin fin and bonded fin type of heatsink. Now heatsink's efficiency is studied by placing PCM, phase change material. V phase change materials, PCM. A PCM is a material which absorbs or releases energy at phase transition to give useful cooling. PCM-based heatsinks effectively store heat dissipated from electronic components and then release energy stored during 0FF period, i.e. when the electronic equipment where the PCM is placed is turned off. 8. Working. The figure 12 explains how PCM works. 8. In this case, initially PCM will be in solid state. With rise in temperature, the PCM starts melting. Once PCM starts melting, the temperature stops increasing as the heat released by chip will be used in melting. Once PCM melts completely, it reaches liquid state, the temperature further starts increasing. So PCM-based heatsinks store heat dissipated from heating component. Further, when electronic component is in off state, PCM solidifies. Fig 12, working of PCM. 8. Using PCM has many benefits like heat storage, no moving parts, compatible to any type of heatsink and is reliable. In present work, all the input parameters including aluminium heatsink are same as that of air domain, but the air as domain is replaced with methylsilyidene, SiCH3, which is chosen as phase change material. Methylsilyidene, SiCH3, is an organic compound with very effective heat absorbing capacity as it can freeze without cooling during crystallization. The figures 13 and 14 show the results for using PCM along with heat sinks. The inlet temperature for bonded fin type heatsink is 17.8390 C and outlet temperature is 20.910 C. Fig 13. Temperature distribution using PCM for bonded fin type heatsink. The inlet temperature for cylindrical pin fin type heatsink is 17.8390 C and outlet temperature is 23.490 C. The inlet temperature for square pin fin type heatsink is 17.8390 C and outlet temperature is 22.040 C. To calculate convection heat flow, let heat transfer coefficient, H, for convection with PCM as fluid is 200 W/m2.K referring to Table 1. The heat flow for different types of heatsinks are as Table 3. From above table, it is noticed that the temperature difference between inlet and outlet is decreasing from cylindrical type of heatsink to bonded fin type of heatsink, and the temperature difference between inlet and outlet is more when compared to Table 2, which is the result of heatsink placed in air domain. The cylindrical pin-fin type of heatsink reduced the temperature of chip by 5.6610 C. Similarly, square pin-fin and bonded fin type of heatsink reduced the temperature of chip by 4.2010 C and 3.0710 C respectively. Hence again, cylindrical pin-fin heatsink acts more effectively in heat removal than square pin-fin and bonded fin type of heatsink. By comparing the Table 2 and Table 3 IE results for air and PCM as cooling medium, we can notice that the temperature difference between inlet and outlet is more by 7.83% for cylindrical pin-fin type of heatsink, 7.89% for square pin-fin type of heatsink, 8.99% for bonded fin type of heatsink by using PCM as cooling medium than that of air as cooling medium. Hence using PCM along with heatsink increases heat removal efficiency of heatsink. From Table 4, it is noticed that outlet temperature for all three types of heatsink is more by using PCM as domain for cooling purpose. Hence it is proved that by integrating PCM, more heat can be absorbed from heating component, compared to that of using only heatsink in electronic devices. Heat dissipated can be removed effectively using PCM. Main motive of the paper is to provide some brief knowledge about the efficiency improvements that can be made in pin-fins to increase heat transfer rate. Main motive of the paper is to provide some brief knowledge about the efficiency improvements that can be made in pin-fins to increase heat transfer rate. Main motive of the paper is to provide some brief knowledge about the efficiency improvements that can be made in pin-fins to increase heat transfer rate. Main motive of the paper is to provide some brief knowledge about the efficiency improvements that can be made in pin-fins to increase heat transfer rate. Main motive of the paper is to provide some brief knowledge about the efficiency improvements that can be made in pin-fins to increase heat transfer rate. 6. Conclusion. The main motive of this work is to provide a comparison of performance of heatsink placed in air and fluid domain, PCM, and improving efficiency of heat transfer rate in pin-fin and bonded type of heatsink by using PCM as fluid medium. After investigating temperature distribution in different types of heatsinks for two types of cooling medium i.e. air and PCM, Table 2 and Table 3, it can be said that 1. Integrating PCM, phase change materials, with heatsink can improve cooling performance, Table 4, and hence efficiency of heatsink can be increased. 2. Comparing performance of three types of heatsinks i.e. cylindrical pin-fin, square pin-fin and bonded fin heatsink both in air and PCM domain, Table 2 and 3, cylindrical pin-fin type is more efficient than square pin-fin and bonded fin heatsink.